The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. When you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. Well, today we're going to take a look at section 11.5, but first, do you have any questions from 11.4?
No, I did not.
All righty, so let's go on to section 11.5. So we've talked about log base 10, which the notation for is just log, also referred to as common log, because log base 10 is used quite frequently when we're dealing with logarithms. There's another base that is commonly used, and that is e. Now, e looks like a variable, but it's not. It represents a number. But before we talk about that, let's go back and talk about pi. Pi is used when we're dealing with circles, circumference, area of circles, diameter, etc., etc. Pi is approximately 3.14. E is approximately 2.71828, or even just approximately 2.7. E is used when we're dealing with a population that is either growing or decaying continuously. Let's take Yakima County, for instance. I don't know what the population of Yakima County is, but is this the way the population growth or decay works? Nothing happens from January 1st up until December 30th, right? And then all of a sudden on December 31st, there's a whole bunch of babies born and a whole bunch of people die. Is that how that works?
Yes,
No.
but it can't be just like nobody dies within 4 months. I'm pretty sure somebody has to die.
So then the answer would be no. It's not like on December 31st and no other time do people get born or people die. It's a continuous process, right? Daily, you can open up the newspaper and see, oh, these people died, these people were born. So a population of people or animals or whatever is a continuous process. So if a population is increasing, it would be increasing on a continuous scale, or if it's decreasing, it would be decreasing, okay? It's not like all of a sudden population grows, all of a sudden the population dies. When that's true, when we're dealing with a situation where the change is continuous, we use the number e, which again is approximately 2.7, all right? Now, we're gonna look at some graph situations, and I'm just gonna do some rough sketches, and then if you need more information, I will go into that. But let's say we graph y equals 2 to the x, okay? And we go through and we make a table, and we produce the graph, and it looks something like that, okay? Then let's say we graph y equals 3 to the x. It tends to look like that. In other words, it climbs steeper, faster kind of thing. Okay, now y equals e to the x, because e is approximately 2.7, it would be right about here. Okay, so graphing y equals e to the x, again, e is just a number, approximately 2.7, would look very similar to y equals 3 to the x. All right, now, how do you get e on your scientific calculator? Okay, so there is a button that we talked about yesterday that says log, and the second function is 10 to the x, okay? Right below it, there is a button that says ln, and the second function of that button should be e to the x. So if you've got a calculator with you, see if you can find that. Do any of you have a calculator with you?
Yes, mine's pulling up e caret, then parenthesis.
Yes. Okay, so you're going to hit your second function button, e to the x, you're going to hit e caret parentheses. Good. So let's just say we want e. So we would put an exponent of a 1 in there. So e to the 1 power, see here, second e to the, helps if I push the right button. I think I better put my glasses on here. Okay, second e to the 1 power. I'm getting 2.718281828. That's on my calculator. Now, it looks like that 1828 is repeating, but actually if the calculator went beyond that, it doesn't repeat. It just has those 4 numbers repeated that once. But again, this is approximately 2.7, okay? So if you need to find E, you can put e to the 1 power, push equals, it'll give you a decimal approximation. If you need e squared, you'd put e to the 2nd power, et cetera, et cetera. Are you okay with that? Any questions there about finding E?
I'm fine.
All right, now, log base E is also used quite frequently, just like log base 10. Well, log base E is called natural log. And why they call it that, I don't know. But because of that, the shortcut notation they use is LN. I suppose it's like log de natural or something. I don't know, whatever. But so my point is, when you see this, you need to think that. When you see this, you need to think that. Now, why don't they just use this and this? Because mathematicians, just like any other group, if there's something that's used over and over and they can shortcut a notation, they tend to do it, okay? But LN, natural log, means log base E. Now, on your calculator, since the second function of LN is e to the x, that should remind you that this is log base E, whereas the second function of log is 10 to the x will remind you that log is log base 10. All right? Now, just a minute here. We're going to do, oh, I know what I want to talk about. So there's a compound interest formula that we looked at that said A equals P times the quantity 1 plus R over K to the KT power. Do you remember that formula from the other day, hopefully?
Yeah.
Okay, when we're dealing with, say, interest being compounded continuously or a growth or decay situation of a population, we use this formula, A equals P times E to the RT power, or I like to call it the PERT formula. Does anybody use PERT shampoo? I think it's still out there. Anyway, but this is not PERT, it's P times E to the RT power, okay? And this R is the same as this one, this T is the same as this one, this P is the same as this one, but all the rest of it gets replaced with the number E. So again, we've got this formula, A equals PE to the RT. We're going to use that on population growth and decay, and we're going to use that when something is compounded continuously as opposed to annually or semi-annually or quarterly or monthly or daily, whatever. Okay, now, so let's take a look at an example. It says, use this formula given the following values of P, R, and T. So let's say that P is 5,000, R is 8%, which we would write as 0.08, and T is 20 years. So we want to find A. So A equals 5,000 times E raised to the 0.08 times 20. Now, we can take 0.08 times 20, predetermine that and go from there, or we can just do the whole calculation all at once. If we're going to do it all at once, we have to be sure to put parentheses around that entire product of the exponent. So again, you can predetermine that and go from there, or you can just do it all at once. So doing it all at once, in my calculator, I'm going to put 5,000 parentheses, oops, no, I don't need parentheses, 5,000, and then second e to the, and I'm going to have 0.08 times 20, close it up, and I get the following: 24765.16212. Now, it says round to the nearest hundredth, which would be right there. The 2 would round down, so I get 24,765.16 would be the answer. Any questions about that particular problem? All right. Let's take a look at another example. Here it says, let's see, P is 15,895. R is -2%, which would be -0.02. And T is 16 years. So the growth rate is negative, which means in fact it's going to decay. So our final value, A, should be less than our initial value, P, because it's decaying at a rate of 2%. All right. So A equals 15,895 times E raised to the -0.02 times 16. Okay. So 15,895, second e to the x, -0.02 times 16, close it up. I get 11,542.138. So again, rounding to the nearest hundredth, A would be 11,542.14. And again, notice that A is smaller than P because it's decreasing at a rate of 2%. Any questions there?
No.
All right. Now it says evaluate each expression without using a calculator. And we have the natural log of E squared. Now, I need to figure out what that's equal to, but without punching it into my calculator. So I'm going to say it's equal to some unknown quantity that I'm going to call box. All right. Now, ln is the same thing as log base E. So I have log base E of E squared, right? So this became that, and this is still there, okay? So log base E of E squared equals box. If I take that logarithmic equation and write it as an exponential equation, the base would be E. So E to the box equals E squared. Do you see how I got from here to there?
Can you explain how you got there?
Okay, so this goes back to yesterday, the idea that if we have, let's say, log base 2 of 3 equals x, we change that to an exponential equation, we get 2 to the x equals 3. The base is the same, the other two numbers change places.
Yes, yes, yes.
Okay, so here the base is the same, the other two numbers change places.
Oh, okay. I see.
Alrighty, you bet.
There's too many E's and I got
I
confused.
know,
Yes,
I know.
got it.
This problem isn't too easy. Okay, so the box equals 2. So the natural log of e to the second power is 2. All right. We good to go on?
Yes.
The natural log of 1 over e cubed. Evaluate this expression. Well, that's equal to some unknown quantity, but ln is log base e. So we have log base e of 1 over e cubed equals some unknown quantity. I'm going to change this logarithmic equation into an exponential equation. So the base is the same, but the players change places. Okay. But I could take 1 over e to the 3 power and write it as e to the negative 3 power by moving it upstairs. So the box equals negative 3. Okay with that?
Yes.
All right. The natural log of the 5th root of e. Well, this is equal to some unknown. Okay. So this is the same thing as log base e of the 5th root of e. Okay. Which means e to the box equals the 5th root of e. But isn't the 5th root of e the same thing as e to the 1/5 power? The index becomes the denominator of the exponent. Remember that? From here to here. That goes back to chapter 9.
Yes.
So the box equals 1/5. All right. Now let's take our calculators back out and using the calculator, evaluate the following. The natural log of 0.675. So on your calculator, hit the ln button, not the second function. We don't want e to the x, we want ln. 0.675, close it up, and I'm getting negative 0.39304. It says round to 4 places, so 4 decimal places, the 4 would round down, so I'd get negative 0.3930 would be the final answer. Okay with that?
Yes.
Okay. How about the natural log of 2.7? I'm getting 0.99325. So rounding at the 2, the 5 would round up, 0.9933. And one more, how about the natural log of negative 10? I get, it says error, non-real answer. Why is that? Have we talked about how you can't take the log of a negative number? Did we discuss that yesterday?
I don't think so. Mine says domain error.
Yeah. Okay, and I'm using a graphing calculator because all my scientific calculators are locked up in my classroom and I can't get there. All right, well, let's talk about that idea. So y equals b to the x. I'm going back to section, I think it's 11.3. We talked about how the base can't equal 1. The base has to be greater than 0. Okay, and x can be what? Any real number. Actually, I should use parentheses there. And y is greater than 0. We talked about the domain and range. Do you remember that?
Yes.
Okay, so if I take this and I rewrite it in logarithmic form, this b is that b. Okay, which means since the base can't equal 1 and has to be positive, log base b, the base can't equal 1 and it has to be positive. Okay, let's take a look at this x. Well, this x is that x. The domain here can be any real number. So your answer can be any real number. Okay, but now let's take a look at this. What do we know about this? That has to be positive, greater than 0, right? But that's right here, which means when we take the log of a number, that number has to be greater than 0.
Does that apply all the time?
Yes,
Okay.
it applies all the time to logs. So Your base has to be positive, not equal to 1. The quantity you're taking the log of has to be greater than 0, but the answer can be positive or negative, could be any real number. So back here, we can't take the natural log of -10. That's why it gives us a domain error or whatever your calculator says on that. All right? Okay. We're going to look at a problem that says continuous compound interest. The key word there is continuous. So that tells us that rather than using this, instead, we're going to be using that because it says continuous compound interest. All right, that's the key. An initial investment of $2,000. So we're not going to use that one. Earns 8% interest. Compounded continuously. What will the investment be worth in 15 years? So A is the unknown. We know P, we know R, we know T. And of course, E is not a variable, it's a number. So A equals $2,000 times E raised to the 0.08 times 15. And let's see here. So we've got 2,000 second e to the x, 0.08 times 15, close up the exponent, 6,640.233. Now, it doesn't say, but since we're dealing with money, you would round to the nearest cent. The 3 would round down. So $6,640.23 would be the final answer. Are you okay with that?
Yes.
All right. Let's take a look at another example. It says determining the previous balance. An account now contains $3,610 and has been accumulating interest at 8% annual interest, compounded continuously. How much was in the account 4 years ago? Okay, it said it was compounded continuously, so that means we're going to use this formula, okay? But now it doesn't tell us the beginning amount, it tells us the ending amount. It says an account now contains $3,610 and has been accumulating interest at 8%. Annual interest compounded continuously. How much was in the account 4 years ago? All right, so we're working backwards. So $3,610 equals P times E raised to the 0.08 times 4. Times 4 years. Okay. Well, now I'm trying to solve for P. So what I'm going to do next is I'm going to predetermine what 0.08 times 4 is, which is 0.32. Okay. And the reason I want to do that is because now to isolate P, I'm going to divide both sides by e to the 0.32 power. So I get P equals $3,610 divided by e to the 0.32 power. Okay, see how I did that? So now on the calculator, 3610 divided by e to the 0.32 power, and I get 2621.398, which is going to be money. Rounding to the nearest tenth, the 8 would round up. So I'd get 2621.40. So if you invested this much at 8% for 4 years compounded continuously, you'd end up with that much. But here they're having you work backwards. So we had this at the end. How much did we start with? Is what that's asking. You all right with that?
Yes.
Okay. Let's talk about bed bugs. It says, if not checked, the population of a colony of bed bugs will grow exponentially at a rate of 65% per week. If a colony currently has 50 bed bugs, how many will there be in 6 weeks? All right, so we're talking about a exponential growth problem. So we're going to use A equals P times E to the RT power. It says it grows at a rate of 65%, and that's per week. If the colony currently has 50 bed bugs, how many will there be in 6 weeks? Now, because it's giving us the growth rate in per week, time is going to be per week. Okay, so the final amount is going to be 50 times E to the 0.65 times 6 weeks. Okay, now let me write that again a little better here. So raised to the power 0.65 times 6. So 50 second e to the x, 0.65 times 6, close it up, and I get 2470.1, rounding to the nearest bed bug, 2,470 bed bugs. If that doesn't make you lay awake at night, I don't know what will. Okay with that?
Yes.
Okay. Here is another example. It says the Big Easy, and I'm not sure if that's a reference. It's talking about New Orleans. I don't know if that's a name for it or what, but it says New Orleans, is it New Orleans or New Orleans? I guess it depends on where you're from, has steadily won back some of the population it lost in the wake of Hurricane Katrina in 2005. If the current 8.2% annual increase in population remains constant, how long will it take for its population to double? All right, so A equals P e to the RT, because we're talking about a population, so it's going to grow or decay at a steady rate. It says it, in fact, it says it remains constant. Okay, it says the current 8.2% annual increase in population. So R is 8.2% or 0.082. How long will it take for the population to double? So the question is, how long? Well, there's a problem here because they don't tell us the initial population. They just say, how long will it take for it to double? So the initial population, I guess, is just going to have to be plain old P. Okay? Because we don't have any additional information. But we do know this. The ending amount is going to be twice as much as the starting amount. So A would equal what in terms of P?
I want to say 2P.
Well, then do, because it's correct. So there you go. Okay. Now, Again, we might be thinking, but we still don't know what the population is. As we're going to see, it doesn't matter. Putting this information into the formula, we get 2p in the place of a equals p times e raised to the 0.082 times t power. Okay? Now, the next thing I'm going to do is divide both sides by p. And voila, it's gone. So we didn't need it. Just the fact that it was going to double was all we needed. Okay with this?
Yes.
So now we're solving for t, but where is t? It's an exponent. How do we isolate an exponent? Logarithms. So this exponential equation is going to become log base e of 2 equals 0.082 t. Remember, we're trying to solve for the time. How long will it take for the population to double? But isn't log base e just ln, natural log? So the natural log of 2 is 0.082 times t. What do I need to do now to solve for t?
Divide both sides by t.
No, we want to isolate t.
Oh, divide both sides by 0.082.
Right, by the coefficient of t. So t equals the natural log of 2 over 0.082. And we put that into our calculator. The natural log of 2, close it up, divided by 0.082. And we get 8.45301, etc. And let's see what it says. It says they rounded to the nearest tenth. So if we round to the nearest tenth, the 5 in the 100th spot would round up and we'd get 8.5 years. So given a population growth of 8.2% annually, it would take approximately 8.5 years for the population to double. Okay? Now, let's take a look at this. What were we trying to do? We were trying to double the population, and notice that we're taking the natural log of 2. And this number down below, where did that number come from? It was r. Okay, there's a formula that says this: t equals the natural log of 2 over r. That tells you how much time it takes to double a population when you know the growth rate. So in other words, we could have saved all of this work and just gone straight to this, knowing about this formula. But that's why I'm telling you about this formula now. All right, let's apply this formula to the next problem. It says, doubling money. How long will it take $1,000 to double if it is invested at an annual rate of 5% compounded continuously? Now, the key there, it has to be compounded continuously. So how long will it take to double money at a rate of 5% compounded continuously? So I can go straight to that formula. Natural log of 2 divided by 0.05, and it's going to be 13.86, so approximately 13.9 years. Now, I did that the short way. If I were going to do it the long way, it would look like this. We'd have, let's see, doubling it, so we'd have 2p equals p e to the 0.05 times t. We would divide both sides by p. 2 equals e to the 0.05 times t. We'd change it into a let's see, that's supposed to be a 2, a logarithmic equation. So we get the natural log of 2 equals 0.05t, divide by 0.05, t equals, you see what I'm saying? So,
Yeah, like
okay,
your
what if we were going to triple it? What would this formula look like?
log to the third.
Yeah, natural log of 3 over r. Okay. Let's see if there's anything else that I want to tell you. I think that should be enough to keep you busy. So I will be back at 1:15 if you have any other questions. Otherwise, have a great